Hello everyone, I'm Ravi Yadav. I'm here to present the paper CNN-based color and thermal image fusion for object detection in automated driving. I have done this work as part of my master thesis in Trinity College Dublin under the guidance of Professor Rozenn and in collaboration with Value. In automated driving, camera is the primary sensor. It is used in ADAS system from more than a decade. It gives a sense of outside environment to the vehicle in form of geometrical information and the semantics. And due to this reason, the major task for the camera is object detection. However, the object detection performance degrades under the different circumstances like weather and the light conditions. An automated vehicle requires different information like nearby objects, the location, the lane markings, traffic signs, and all these informations are provided by different sensors like GPS, ultrasonic, radar, LiDAR, and cameras. The focus of this research is typical RGB camera and the thermal camera. In past, researchers focused on creating good classifier detectors for color images, which perform really well under good lighting condition. However, their performance degrade at night time. They are sensitive to the illumination changes. And it is due to this reason researchers focused on new direction to fuse information of a visible camera that is RGB with the information provided by long wavelength infrared cameras that is thermal. The thermal cameras omit the need for external light source and also less affected by bad weather condition. It is due to all these reasons I can say thermal sensors are complement of color sensors. They are already used in production vehicle for the night vision and focus of this research is to see how effectively thermal and the RGB camera can detect the object even in the night condition. The major contribution of this paper is to create a simple fusion architecture and baseline with the two unimodels that is RGB unimodel and thermal unimodel. Later, study all three networks for the day and night condition separately and in the end analyze their results on two most famous multispectral datasets KAIST and the FLIR. Multimodal fusion is really common in autonomous driving. They makes the system more reliable and safer for driving. Very common scenario of using is radar and the camera data or the LiDAR and camera data. It is only after the introduction of KAIST dataset in 2015 the research focused on fusing the thermal and RGB cameras for increasing the accuracy of object detection during different weather and light conditions. After 2015, many research has been done to creating these architectures the complex one. Here is the example of one of the architecture for the multispectral object detection. In this architecture, the input is color and the thermal images for the object detection. Now, this architecture seems to be really complex and focus of our paper is to achieve the similar results of the state of the art with a simple architecture. In our paper, we propose three models. First two are unimodels which are used as a baseline. So for the first model, RGB image is an input which is provided for the object detection. In the second model, thermal image is provided as an input to the unimodel. And in the third, RGB and thermal images are provided in input parallelly whose feature map are concatenated and then provided for the decoder for the classifier to do the object detection. Now, talking about the unimodal architectures, the two unimodal architectures were trained first on using RGB images, second using only thermal images. The purpose of creating unimodal baseline networks is to evaluate the contribution of individual cameras with the fusion architecture. For this purpose, Foster RCNA networks was used as a SOTA for object detection. The training of the thermal or the RGB was done using the VGG16. The idea here to keep the network simple, and it is due to this reason we adopted the VGG16. Input signal is fed into VGG16 encoders where the output features are used to generate object proposals through RPN. ROI generated from RPN is fed into ROI pooling and classification stage for the final output. All these things were common in thermal and the RGB networks. In this paper, we focus on network-based multispectral fusion. Object detection is less explored for multispectral data for autonomous driving. It is widely used in other vision tasks such as semantic segmentation, object classification, etc. However, some of the work like introduction of gated fusion layer combining RGB and depth stream is an example of fusion. There are different levels of fusion. Talking about levels, first input fusion where you simply stack the color and the thermal images before feeding them into the network. Early fusion where we integrate color and thermal at the subnetwork right after the first convolution. Half fusion where we combine color and the thermal subnetworks at the later stage, let's say around fourth or fifth convolution block, so that we can combine and concatenate the features. And fusion is a kind of high level fusion which concatenate last fully connected layer from the color and thermal subnetworks. In this paper, we construct two-stream network which utilizes parallelly VGG16 encoder to extract the appearance and the thermal features separately. Our main goal is to combine these separately identified features using the concatenation function or summation junction in the last convolution layer of the output. The same decoder is used as we have used in Unimodal Baseline to generate the final prediction. For the purpose of our research, we use two datasets, that is KAIST and FLIR dataset. KAIST dataset is multispectral pedestrian detection dataset which was released in 2015. It contains more than 95,000 aligned RGB and thermal images. It is one of the dataset which is used for benchmarking the fusion architectures. Next, the latest released FLIR dataset which also contains thermal and RGB images. This dataset's images were synced, however, their aspect ratio were different and the RGB images were not annotated. Due to this reason, we tried to perform the computer vision techniques to align these images, but due to the absence of intrinsic parameters from the cameras, those efforts were not performed really well. Therefore, later on we only benchmark our network performance on only in KAIST. Next, talking about the experiments, we use all the default settings in all three models, that is two unimodals and one fusion architecture. So Adam optimizers were found to give the maximum performance after the hyperparameter tuning. L2 regularization was done to avoid the overfitting. Encoders were used predefined weights of VGG16 from the ImageNet. Dropout with a probability of 0.5 is utilized on 1 cross 1 convolution layer, and log average miss rate was used as a performance metrics. We did a comparison of our fusion architecture with all other state-of-the-art architecture whose results were available on the KAIST dataset websites and can be validated. Based on our analysis, we found that our proposed fusion architecture performs almost similar to the state of the complex architectures. Now, if we see the comparison of two unimodal and the fusion architecture during different daytime, so talking about the RGB image dataset which performs really well during the day compared to the thermal image during the daytime. During the night time, thermal unimodal perform well enough as compared to RGB. If we consider the complete dataset, that is a combination of day and night time, we see the performance of the fusion architecture combined outperforms the RGB only architecture or the thermal only architecture. These are the results what we get after the object detection from the three networks. On the left hand side, it shows the nighttime results, and on the right, it shows the dusk results. On the night time, if you see that this particular image, which is RGB, is not able to detect the pedestrian, wherever the thermal image data can detect the pedestrian. And next, talking about the fusion one, all these pedestrians were also detected in the fusion. In this video, we can clearly see how the pedestrian is not able to detect in RGB networks, but it is visible in infrared and as well as in the fusion architecture. So this is an example how autonomous vehicle can be benefited by using a simple fusion architecture like this. To conclude our work, fusion network outperforms the individual baseline networks. The obtained results on KAIST dataset were very near to the state of the art, keeping our network very simple compared to the state-of-the-art networks that use segmentation and the weighted fusion. That makes the network more complex. Third, in our model, we also tried to implement this fusion on the FLIR dataset, but due to the limitation of FLIR dataset, it was rejected. Next, talking about the future work, first, it would be interesting to create a simple elimination aware architecture. Second, to compare the inference rate of different fusion architectures on the hardware. And third, to do the object detection of fusion architectures using the thermal, RGB, and radar, or thermal, RGB, or LiDAR. Following are the reference which I used during the research. To discuss more about this work, feel free to connect and ask questions. In the end, I would like to thank my co-authors and mentors for the motivation, Professor Rozenn, Senthil, and Hazem from Value.